Have you ever had a moment where the entire world seems to pause? As if everything around you knows something monumental is about to happen, something that will redefine how humanity understands itself? Imagine it, a quiet laboratory in Cambridge, papers scattered across a desk, a rough model made of bits of metal and cardboard, and two scientists pacing, arguing, reassembling, and suddenly stopping. Because in that instant they see it, a shape that isn't just beautiful, but life-defining. A structure that explains heredity, evolution, disease, and ultimately, what makes you, you. That structure was the double helix, and today, you and I are going to step inside the discovery that changed biology forever. Before we dive in, make sure to like this video, subscribe to the channel, and hit that notification bell so you never miss another deep dive into the papers that built our world. It really helps us out and keeps this project going. Now, let's begin the story. When James Watson and Francis Crick published their short, almost deceptively simple 1953 paper titled Molecular Structure of Nucleic Acids, a Structure for Deoxyribose Nucleic Acid, they were not just describing a molecule. They were laying out a blueprint for how information is stored, protected, copied, and transmitted across generations. But the magic of this paper isn't only in what they concluded, it's in how they pieced the evidence together, drawing on chemistry, X-ray diffraction images, and a few bold, brilliant assumptions. The paper opens with an understated line. They wish to suggest a structure for DNA. But what follows is arguably the most important single paragraph in the history of biology. Watson and Crick propose that DNA is made of two helical chains, coiled around a common axis, winding together like a twisted ladder. Each chain is composed of repeating sugar phosphate units. These phosphates lie on the outside, forming a sturdy backbone. The bases, adenine, thymine, guanine, cytosine, sit inside, perpendicular to the helix axis, arranged in pairs. But here's the trick. The bases pair in only one specific way. Adenine with thymine, guanine with cytosine. This is the key that unlocks everything. From this pairing rule, a breathtaking implication falls out naturally. If you know the sequence of one chain, you automatically know the sequence of the other. The two strands are complementary. They contain the same information, encoded in opposite forms. And because they are held together by hydrogen bonds, weak enough to separate, strong enough to stay paired, they can unzip. They can replicate. They can pass information to new cells with astonishing fidelity. But Watson and Crick didn't arrive at this structure in a vacuum. The X-ray diffraction image that contained the crucial geometric clues, image B, taken by Rosalind Franklin and Ray Gosling at King's College, showed a pattern so unmistakably helical that even someone who had never seen DNA before could follow the repeating X-shaped pattern across the film. On page 2 of the PDF, the fiber diagram displays the telltale signatures, the angle of the streaks corresponding to the helix, the spacing of the layer lines indicating a pitch of about 34 angstroms, and the strong 3.4 angstrom reflection that signaled some repeating internal unit, later understood as the spacing between adjacent stacked base pairs. Franklin's meticulous work showed that DNA could exist in multiple structural forms depending on humidity, her so-called structure A and structure B. Structure B, the more hydrated form, produced the image that Watson saw, and that Crick mathematically understood through Bessel function calculations. On page 3, you can see the complex mathematical reasoning. The pattern of intensities along each layer line fits a helical transform, and the especially strong 10th layer line, where the famous 3.4 angstrom reflection appears, suggested 10 repeating units per turn of the helix, 10 bases, 1 full twist, 34 angstroms. Everything fit. But let's take a moment here, not just to admire the elegance of the math, but to appreciate how unlikely this discovery was. Imagine handling a substance, sodium thymonucleate, that looks like a sticky, translucent fiber. You stretch it, you dry it, you hydrate it again. You expose it to X-rays, and you capture the faintest scattering of photons onto photographic film. And from that pattern, people like Wilkins, Stokes, Wilson, Franklin, and Gosling could deduce the very architecture of life's information system. Picture the photograph on page 4 of your PDF. A soft, circular blur toward the outside, but a striking X shape in the center, the helical signature. That image carried the weight of decades of chemical mysteries. But what exactly were they seeing? To understand that, we need to step inside the helix itself. Imagine shrinking down to the molecular scale, floating between the two spiraling backbones. The sugar-phosphate chains form the rails, and in the center you see the bases stacked like a pile of coins, each separated by about 3.4 angstroms. The bases aren't randomly placed, they're perpendicular to the helix axis, maximizing their interactions through pi stacking, which stabilizes the entire structure. The helix is not loose, it is not floppy. It is elegant and rigid enough to protect the genetic code from random distortions, while flexible enough to be read and copied. Now, from the X-ray evidence, several curious details emerged. One was the consistent diameter, about 20 angstroms across. That meant the bases couldn't pair arbitrarily. A purine pairing with a purine would be too wide. A pyrimidine pairing with a pyrimidine would be too narrow. Only purine-pyrimidine pairs create the perfect, constant width. And if they were paired regularly, they must be paired specifically. This is where Chargaff's rules, adenine roughly equals thymine, guanine equals cytosine across species, click perfectly into place. But Watson and Crick didn't need Chargaff's explanations to be perfect. They simply needed the insight that complementary bases allow the structure to explain heredity. Because if one strand is the template for the other, the genetic code becomes self-replicating by design. And that's where the story becomes even more astonishing. Watson and Crick's model did more than just explain what DNA looks like, it explained how it behaves, how it copies itself, how mutations occur, why genetic information remains consistent, and how it can change. In the paper, they wrote, almost casually, something along the lines of, "It has not escaped our notice that the specific pairing immediately suggests a copying mechanism." That sentence may be the single greatest understatement in scientific literature. Now let's zoom back out and see how their model compared with earlier attempts. Other scientists, like Pauling and Corey, had proposed triple helical structures, even forming models where phosphates sat at the center. But Franklin's data immediately made that impossible. As described on page 5, the phosphate groups must be on the outside because their density distribution aligns with the helical maxima in diffraction patterns. The bases must be inside, shielded from water. And the asymmetry in layer line intensities suggested 2 chains, not 3. In other words, the double helix wasn't just elegant, it was the only model that fit the evidence. As fibers were stretched, as shown in the Stokes and Wilkins analysis, the helix extended like a spring. The sugar-phosphate chain was in an almost fully extended state already, meaning the structure was both strong and flexible. The bases, arranged like a pile of pennies, built a hydrophobic core that stabilized the molecule's interior. Franklin and Gosling went further in their analysis, describing 2 distinct forms that DNA could adopt depending on hydration levels. On page 4, they discuss how structure B emerges when the fibers absorb water beyond a certain threshold, and how the helix adjusts its geometry accordingly. They show that the phosphate groups are clearly on the outside, since these are the parts of the molecule that interact strongly with water. This observation aligns perfectly with the pattern in the diffraction diagram. Strong equatorial reflections indicating dense material at the helix's outer radius. All of this evidence, physical, geometrical, chemical, came together to paint a single coherent picture. But let's not forget something important. This discovery wasn't made by just 2 people. The images and data produced by Rosalind Franklin and Ray Gosling were absolutely crucial. Maurice Wilkins and his collaborators had long been exploring nucleic acids through fiber diffraction. Stokes and Wilson had developed foundational mathematical models for helix diffraction patterns. The combined expertise of these groups created the framework within which Watson and Crick could propose their bold, beautiful, correct structure. And what does this mean for us, today? Think about your body right now. Every cell contains DNA. Billions of nucleotides arranged in a very specific order. The double helix makes this possible because it allows DNA to pack enormous amounts of information into microscopic volumes. The stacking of bases, the stability of hydrogen bonds, and the outward-facing phosphate backbone collectively form a molecule that is at once protected and readable. Without that arrangement, there would be no reliable system for heredity, no natural selection, no evolution as we know it. The double helix explains why children resemble their parents, why species persist, how traits and diseases are passed on. It explains how viruses store their genetic code. It explains how cells divide, how proteins are built, how life adapts, survives, evolves. This single paper began a biological revolution. But let's return for a moment to the simplicity of that structure. 2 strands, a sugar phosphate backbone, 4 bases, and rules, pairing rules, that lock the entire biological universe into place. For all the complexity of life, these building blocks are astonishingly small and beautifully ordered. The story doesn't end with the paper, of course, but in that moment, in 1953, Watson and Crick crystallized the fundamental architecture of life. Their insight allowed scientists to decode genomes, understand mutations, engineer organisms, diagnose diseases, and create treatments. It laid the groundwork for biotechnology, CRISPR, synthetic biology, and so much more. But everything, absolutely everything, begins with the structure described in that short, revolutionary paper, and with the diffraction patterns and mathematical reasoning presented in the accompanying work from King's College. Before we wrap up, imagine again the photograph on page 4, a ghostly image of concentric circles and an X-shaped cross. At first glance, it looks like an abstract piece of art. But hidden inside that image, captured in a dim laboratory in early 1953, is the blueprint of life. It's almost poetic, a blurry photograph of scattered X-rays revealing the order that underlies every living thing. And that is the power of scientific discovery. To look at something ordinary, like a smudge of light on film, and to see the entire mechanism behind life as we know it. If you enjoyed this deep dive into the paper that transformed biology forever, please make sure you like this video, subscribe to the channel, and leave a comment about which classic scientific paper you want us to decode next. Your engagement truly helps this channel grow, and it tells the algorithm that people want more intelligent, story-driven science content. Thanks for watching, and stay curious, always.